Hi guys, this is Computer Networks and Security Special Module, TCP/IP Protocol Suite, IP Addressing and Subnetting for CCNA2 Routers and Routing Basics. This is a special module taken back from CCNA1, Module 9 and 10. Please listen and make sure to jot down notes or replay this video to cope up with the discussion. As the discussion progresses, there may be languages in Tagalog to further explain the topic. Enjoy! Upon completion of this module, the student will be able to perform tasks related to the following: Introduction to TCP/IP, Internet addresses, and obtaining an IP address. Introduction to TCP/IP. Any devices on the Internet that wants to communicate with other Internet devices must have a unique identifier. This identifier is known as IP address. The explosive growth of the Internet has threatened to deplete the supply of the IP addresses. This is known as IP address scarcity. Due to IP address scarcity, several solutions have been developed to expand the number of IP addresses available for public use. It can be through subnetting. We will discuss subnetting in next following slides. Network Address Translation, or NAT. NAT uses something called a port number. You can have a total of 65,535 TCP ports and another 65,535 UDP ports. NAT is a process of modifying IP addresses information in IP packet headers while in transit across a traffic routing device. Private addressing. A private network is a network that uses private IP address space. These addresses are commonly used for home, office, and enterprise LANs when globally routable addresses are not mandatory or are not available for the intended network applications. Usually, this is something like 172.x.x.x or 192.168.x.x. We will further tackle that on next topics. IPv6. It is another version of IP address. To check for the IPv6, go to your control panel, Network Connections, select a network interface. Go to IPv6. IPv6 is the latest version of the Internet Protocol or IP. It is intended to replace the older IPv4. Classless Interdomain Routing or CIDR. It is a method of allocating IP address and routing Internet Protocol packets. Their goal was to slow the growth of routing tables on routers across the Internet and to help grow the rapid exhaustion of IPv4 addresses. This is the TCP/IP model developed by US Department of Defense or DoD. Layer 1, Network Access. Layer 2, Internet. Layer 3, Transport Layer. Layer 4, Application layer. Let's discuss first the upper layer down to the first layer, application. Application layer handles high-level protocols, representation, encoding, and dialog control. The TCP/IP protocol suite combines all application-related issues into one layer. The protocols under the application layer are: for file transfer, TFTP, or Trivial File Transfer Protocol. It is a connectionless service that uses the User Datagram Protocol or UDP. TFTP is used on the router to transfer configuration files and Cisco iOS images, and to transfer files between systems that support TFTP. It is useful in some LANs because it operates faster than FTP in a stable environment. Next is FTP or File Transfer Protocol. FTP is a reliable, connection-oriented service that uses TCP to transfer files between systems that support FTP. It supports bidirectional binary file and ASCII file transfers. NFS or Network File System. NFS is a distributed file system protocol suite developed by Sun Microsystems. It allows file access to a remote storage device such as hard disk across a network. For email, SMTP or Simple Mail Transfer Protocol. It administers transmission of email over computer networks. It does not provide support for transmission of data other than plain text. For remote login, we use Telnet. Telnet provides a capability to remotely access another computer. It enables a user to log into an internet host and execute commands. A Telnet client is referred to a local host. A Telnet server is referred to as a remote host. Lastly is RLogin or remote login. For network management, SNMP or Simple Network Management Protocol. SNMP is a protocol that provides a way to monitor and control network devices. SNMP is also used to manage configurations, statistics, performance, and security. For name management, we use DNS or Domain Name System. DNS is a system used on the internet to translate domain names and publicly advertise network nodes into IP addresses. Some of the popular domain registers are the following: .com for computer, .net for network, .org for organization, .info for information, .biz for business, .mobi for mobile devices. For regions, .eu, .ph, .us, .asia, .uk, .edu for education, .gov for government organizations. Layer number 3 is transport layer. It provides a logical connection between a source host and a destination host. The primary duty of a transport layer is to provide end-to-end control and reliability as data travels through the network. This is accomplished through the use of sliding windows, sequence numbers, and acknowledgements. The transport layer also defines end-to-end connectivity between host applications. The transport layer protocols include TCP and UDP. The protocols under transport layer include TCP or Transmission Control Protocol and UDP or User Datagram Protocol. When you say connection-oriented, means that when devices communicate, they perform handshaking to set up an end-to-end connection. Connection-oriented systems can only work in bidirectional or two-way communication environments. To negotiate a connection, both sides must be able to communicate with each other. This will not work in a unidirectional environment or one-way. Some protocols under connection-oriented are TCP, SMTP, DCCP, ATM, Frame Relay, STTP, IPX. Hope you research for the acronym of these. When you say connectionless, it means that no effort is made to set up a dedicated end-to-end connection. Walkie-talkies are a good example of connectionless communication. You speak into the mic and the radio transmitter sends out your signal. Example of connectionless protocols are IP, UDP, ICMP, DNS, SNMP, TFTP, HTTP. The functions of TCP and UDP are as follows. They segment upper layer applications data. They send segments from one end device to another. The function of TCP are as follows. It establishes end-to-end operations. It provides flow control through the use of sliding windows. It ensures reliability through the use of sequence number and acknowledgements. Layer 2 is Internet. Its purpose is to select the best path through the network for packets to travel. The main protocol that functions at this layer is IP. IP provides connectionless, best effort delivery routing for packets. IP is not concerned with the content of the packets, but looks for a path to the destination. IP is sometimes referred to as unreliable protocol. This doesn't mean that IP will not accurately deliver a data across a network. IP is unreliable because it does not perform error checking and connection. That function is handled by upper layer protocols, the transport and application layers. Also, the best path determination and packet switching occur at this layer. The protocols under Internet layer are IP or Internet Protocol, ICMP or Internet Control Message Protocol that provides control and messaging capabilities. ARP or Address Resolution Protocol, it determines a data link layer address or MAC address for known IP addresses. RARP or Reverse Address Resolution Protocol, it determines the IP address for known MAC address. The lower layer, layer number 1, is network access. Network access allows an IP packet to make a physical link to the network media. Network access layer protocols also map IP addresses to physical hardware addresses and encapsulate IP packets into frames. Please recall CCNA1 for encapsulation and decapsulation. The network access layer defines the physical media connection based on the hardware type and network interface. The network access layer is also called host to network layer. The physical and data link layer of OSI relate to the network access layer of the TCP IP model. The protocols under network access layer are Ethernet, Fast Ethernet, SLIP and PPP, FDDI, ATM, Frame Relay, and SMDS, ARP, Proxy ARP, RARP. Please get all the acronyms of this. As you can see here is a TCP IP model and OSI model. TCP IP model has network access, internet, transport, application, while OSI layer has physical, data link, network, transport, session, presentation, and application. The OSI and TCP IP models have many similarities. Both have layers. Both have application layers. Both have comparable transport and network layers. Both use packet switch instead of circuit switch technology. Here are some differences of an OSI and TCP models. TCP/IP combines OSI application, presentation, and session layer into its application layer. TCP/IP combines the OSI data link layer and physical layer into its network access layer. TCP/IP appears simpler because it has fewer layers. Now let's move on to more exciting part, IP addressing. For any two systems to communicate, they must be able to identify and locate each other. Each computer in a TCP/IP network must be given a unique identifier or IP address. This address, which operates at layer 3 of OSI, allows one computer to locate one another computer on a network. An IP address is a 32-bit sequence of ones and zeros. To make the IP address easier to work with, it is usually written in 4 decimal numbers separated by dots. This way of writing the IP address is called a dotted decimal format. For example, we say 192.168.1.8 and 192.168.1.9. This decimal format IP address can be converted to a binary sequence like this and vice versa. Take note that we are studying IPv4 address. IPv4 address starts with 0.0.0 and go up to 255.255.255.255. All numbers in between can be assigned as IP address. There are 5 classes available for IP ranges: Class A, Class B, Class C, Class D, and Class E. While only Class A, B, and C are commonly used, each class allows for a range of valid IP addresses. Class A starts from 1.0.0.1 to 126.255.255.254. Having this range supports approximately 16 million hosts on each of the 127 networks. Class B starts from 128.1.0.1 to 191.255.255.254. Having this range supports approximately 65,000 hosts on each of the 16,000 networks, while Class C starts from 192.0.1.1 to 223.255.255.254. This supports approximately 254 hosts on each of 2 million networks. Class D starts from 224.0.0.0 to 239.255.255.255. This is used for multicasting. Class E starts from 240.0.0.0 to 254.255.255.254. Class E reserved for future use or research and development purposes. As mentioned, we will basically focus on Class A, Class B, and Class C. The IP address consists of 2 parts, network part and hosts part. The network part determines the total number of networks, while the host part determines the total number of hosts per network. As mentioned, IP address is 32 bits long. This is divided into 4 octets: octet 1, octet 2, octet 3, and octet 4. Each octet is 1 byte. 1 byte is 8 bits. So in Class A, octet 1 is network part, octet 2, octet 3, and octet 4 are in host part. Class B, network, network, host, host. While in Class C, octet 1, octet 2, and octet 3 belongs to network part, while octet 4 belongs to host part. Take note that an IP address that has binary zeros in all of host bits position is reserved for the network address. An IP address that has binary 1 in all host bits positions is reserved for the broadcast address. Now, this is an example of a Class C IP address. The 192.168.1 belongs to the range of a Class C IP address. In Class C, network part, network, network, host. If all the bits in the host part are zeros, that represent a network ID. If all the bits in the host are zeros, except the last bit, it is the first usable IP address. If all the bits in the hosts are ones, except the last bit, which is 0, this is the last usable IP address. If all the bits in the host part are 1, that represents a direct broadcast address. There are several IP addresses that are automatically assigned when you set up a home network. These default addresses are what allow your computer and other network devices to communicate and broadcast information over your network. Below is the most commonly assigned network address in a home network. In this example, is again a Class C network. Network, host. One is commonly used address called gateway. .2 can be used as gateway as well. As standard, .1 and .2 can be reserved for gateway. .2 to .254, these are addresses that can be assigned on computer or other network devices. .255 is automatically assigned to broadcast address. The network address and the broadcast address are called reserved addresses. Network address and broadcast address are considered as reserved host addresses. Network address is used to identify the network itself. Broadcast address is used for broadcasting packets to all of the devices on the network. This is an IPv4 address that has 32 bits. In this case, this is Class B. Network, host. This is an example of a Class B IP address, 176.10.0.0. This is an example of a network address because all host bits are zeros. Another example in Class C IP address is this one. Network, host. All hosts are zeros, so this is considered as network address. The broadcast address is having all host bits 1. This is another example of a Class B IP address. Network, host. All host parts are 1, that's why it's called broadcast address. 255 in binary is 11111111. Now let's move on to subnetting. Subnetting a network means to use the subnet mask to divide the network and break a large network into smaller, more efficient, and manageable segments, or called subnets. Subnet addresses include the network portion plus a subnet field and a host field. The subnet field and the host field are created from the original host portion of the entire network. To create subnet addresses, a network administrator borrows bits from the host field and designates them as a subnet field. You are assigning some host bits to be a part of a network field. Reasons for subnetting. Manageability. It provides addressing flexibility for the network administrator. Each LAN must have its own network or subnetwork address. It provides broadcast containment and low-level security on the LAN. It provides some security since access to each subnet is only available through the services of a router. Please take note of this simple but complicated formula 2 raised to n minus 2, where n is a power of borrowed bits, x is a usable subnet or usable host, minus 2 is the network address and broadcast address. The same formula is applied in getting the total number of subnets, total number of hosts, and total number of usable hosts. So, in this example, 192.168.10.10 is a Class C network address. This falls in a Class C IP range. This is represented in a binary like this. Say if you borrow 3 bits from the hosts to the network, 3 bits borrowed allows 2 raised to 3 minus n or 6 usable subnets. Example of a Class B IP address is 147.10.0.0. In Class B, network, host. Say you want to borrow 5 bits from the host part and add to the network part, 5 bits borrowed allows 2 raised to 5 minus 2 or 30 usable subnets. Class A network, 28.0.0.0, network, host. Say if you want to borrow 12 bits from the host part to be a network part, so that's 12 bits borrowed allows 2 raised to 12 minus 2 or 4094 usable subnets. To create the subnetwork structure, host bits must be reassigned as network bits. This is often referred to as borrowing bits. However, a much more accurate term would be lending bits. The starting point of this process is always the leftmost host bits, the one closest from the last network octet. Always starts from here. So let's challenge it further. Earlier, I mentioned that IP address starts from 0.0.0.0 down to 255.255.255.255. There are network part and there are host part. Say in this example, you borrowed 3 bits from host part and join it from the network part. So actually, there are 6 usable subnets. In reality, there is 8, 16, 24, 25, 26, 27 bits of the network part. So that's 2 raised to 27 is approximately around 134 million networks within this Class C IP address. But practically, there is no usable subnet, so we can omit this -2 when we refer about subnets or network. Because a subnet can have millions of hosts, so sayang. Here, 5 bits left in the host part, so that's 2 raised to 5 equals 32. That's 32 total number of hosts. -2, which is 30, so that's 30 number of usable hosts. So next here, this is a class B and we borrowed 5 bits from the host part to network part. This is actually 8, 16, 17, 18, 19, 20, 21 bits from the network part. So that's 2 raised to 21 equals approximately around 2 million total number of networks. We borrowed 5 bits, so that's 2 raised to 5, which is 32 number of subnetworks. The remaining host bits are 8, 9, 10, 11, so 2 raised to 11 is equals to 2048. So 2048 total number of hosts. -2 is 2046, which is total number of usable hosts. So we can have 2048 total number of hosts per network, and we have approximately 2 million networks. So 2 million times 2048 is something bigger. Now we move on to subnet mask. This is to determine the total number of bits to be used in a subnet process. The network designer needs to calculate how many hosts the largest subnetwork requires and the number of subnetworks needed. The subnet mask gives the router the information required to determine in which network a subnet a particular host resides. The default subnet mask of a Class A network is 255.0.0.0. Class B has a default subnet mask of 255.255.0.0. Class C has a default subnet mask of 255.255.255.0. Since we are borrowing bits, if 2 bits are borrowed, so that's 11,000,000. In decimal, that's .192. So on and so forth. If 7 bits are borrowed, so 11111110, so that's .254 in decimal. The subnet mask can be represented in a CIDR format, in a slash format. Going back to this example, 3 bits are borrowed. So 8, 16, 24, 25, 26, 27. In CIDR, this is /27. So this can be represented as 192.168.10.0/27. So this means we have the IP address 192.168.10.0. Subnet mask is 255.255.255.224 because it's /27. In Class B, we borrowed 1, 2, 3, 4, 5 bits. So that's 8, 16, 17, 18, 19, 20, 21. /21. So this can be represented as 147.10.0.0/21. So this means we have an IP address of 147.10.0.0, subnet mask 255.255.248.0. In Class A, in our example, we have 18, 17, 18, 19, 20 bits in the network, so that's /20. This can be represented as 28.0.0.0/20. This means that we have an IP address of 28.0.0.0, subnet mask 255.255.240.0. Actually, you don't have to memorize all of these values. If you know how to manipulate the 2 raised to n and 2 raised to n minus 2, you can come up with the total number of subnets, total number of hosts, and total number of usable hosts. And you know how to convert from binary to decimal numbers, so you're good. Calculate the resident subnetwork through ANDing. Routers use the subnet mask to identify the home subnetwork for individual nodes. This process is referred to as logical ANDing. ANDing is a binary process in which the router calculates the subnetwork ID for an incoming packet. ANDing is similar to multiplication. Any number ANDed by 0 results to 0. All ones are ones. In this example, we have an IP address of 201.10.11.65, subnet mask of 255.255.255.224. So converting everything in binary and do the logical AND. So 1 ANDed to 0 is 0, 0 ANDed to 0 is 0, 0 ANDed to 0 is 0, so on and so forth until you complete all the binaries. Bringing it back to decimal will lead you to 201.10. This is called the subnetwork ID or network ID or network address. There are actually two types of subnetting, the full subnetting and the partial subnetting. The subnet starts from the default addresses. Example, you have a class A IP address 10.9.8.7. So the default subnet mask is 255.0.0.0. Doing the logical AND will lead you to 10.0.0.0. Any number ANDed by 0 is the result is 0. This is the network address and the subnetting should start here. If you are given a subnetwork mask, for example, /11 or /18 or so on and so forth, so the division of the network start at this network address. In partial subnetting, this is followed. So this is practical because you don't have to go to the very first IP address that is 0.0.0.0 down to 255.255.255.255. Again, the full subnetting should start at the network address resulted from the default subnet mask, while in partial subnetting, the subnetting should start at the network address resulted from the subnetwork. For the demo about subnetting, please watch my other videos for this. That's it. Ensure you have jot down your notes or play this video again. Make sure to watch other videos to get to know more about computer networks and security. This is Vernon and thank you very much.